Okay.
Okay? Okay, so now you can manage your desktop like you normally do, just don't log out of Blackboard.
Okay.
You got it?
Yep.
Okay, and then when a few more folks get here, if you want to go ahead and get your slides up. And
Okay.
then as your thing on here, your one's on here.
So let's see. This will be my last slide.
Oh, good. I'll just delete everything past that.
Right after that one.
And they're on here?
Yes.
Somewhere? Is there anything on here I'm not supposed to see?
No,
Okay.
It's fine. So there's something that says no SQL, and if you go into that, then there's something that's just no SQL.
And it's
no
PowerPoint.
SQL PowerPoint.
Okay, got it.
And that's almost exactly what I have in here. I think
Okay.
I made some very minor tweaks that have no bearing whatsoever on content.
Okay. And now, if it's okay, can I get you to say a few words about what you do at Oak Ridge?
Sure.
Kind of your specialty.
Yeah.
So that you can articulate.
No, I'm glad to do that.
Awesome.
So.
Okay. Okay, guys. Since we're at 3:30, I'm going to go ahead and start. I have the slides in my hand, so I'm going to be posting the slides in a few minutes as soon as I send them on the Blackboard if folks want them to look at while we're doing the lecture. I'd like to introduce Dr. Mike Leitze. He has joined us before at UAMS in biomedical informatics for lectures in the research seminar series, and to visit and collaborate with department faculty. And he has graciously agreed to give us a lecture on NoSQL databases. He uses some NoSQL in the work that he does. And I'm going to get you also to say a few more words about your research interest and what you do, because I know it's bigger than NoSQL.
Okay.
Meanwhile, I'm going to email out the slides.
Okay. Thanks, Meredith. As Meredith said, I'm from Oak Ridge National Laboratory, and I am the group leader for computational biomolecular modeling and bioinformatics. I will confess that I was group leader for about 6 weeks before I could remember the name of my own group. But we do a lot of bioinformatics work, a lot of biophysics work, and I share a lot of interest with Dave, with Intowat, with Seiron, with Visanu, and some of that I think will come out in the lecture. So, do we need to do something to?
Oh dear.
To get the projector on?
We might need to do something more than I did. Okay, laptop is checked. There we go.
Here we go. Okay, I'd like to start by thanking Meredith for this invitation. As she said, I've done a lot of work with databases, but I've never really done a deep dive into understanding how databases are constructed, how they relate to each other, and just looking at the nuts and bolts, what's going on under the hood with all kinds of databases. And so this was a good opportunity for me to pull a lot of information together. I've really enjoyed putting this presentation together, and you should consider the first 3/4 of it to be kind of like a book report. And then for the last quarter, I get into some of the uses that I have made, particularly of graph databases. Now, I come from the Dave Ussery School of how to make pretty fun presentations. And so, as most of you probably have realized by now, the #1 rule is you have to start with a really good picture. And so here's the picture that I chose. And there's at least one other person in this room that will recognize this picture immediately.
I like that picture. That's old home picture.
So this is a picture from my alma mater, Duke University, the Duke Chapel on campus. So there are a lot of databases, and this is a graphic from 2013 of the database landscape, and it's changed some since then. Some of these have kind of dropped off, and some others have been added. So this is going to be a really, really long presentation. I'm only going to talk about 3 or 4 of them.
Looks like the French Metro, man.
So I'm going to need to stay pretty close to my laptop, because the second rule for pretty fun presentations is you have to have a lot of animation. And I estimate that I probably have about 300 animations in this presentation. Almost all of them are fades, so they don't come up to Dave's standard, but I don't want to give you all the information on a page when I start. So a good place to start talking about NoSQL, NoSQL databases is with SQL and relational databases. So relational databases started about 1970 with Dr. Ted Codd working for IBM, and he came up with a relational model for databases. And his model is based on the process of normalization, which is designed to organize the data and reduce redundancy. So conceptually, what happens with normalization is large tables are divided into smaller tables that are less redundant, and relationships are then defined between tables. The objective is to organize data in such a way that if a modification is required, that modification can be made at one single point in the database, and then that modification gets propagated throughout the database by the relationships that are defined between the tables. The rules for normalization, each rule is called a normal form. If the first rule is followed, then the database is said to be in first normal form. In most cases, third normal form is sufficient, following the first 3 rules for normalization. Now, here's an example. So we have this unnormalized table, and the problem with this table is we have these repeating groups. We have 3 different columns for class. So what happens if somebody comes along and wants to take 4 classes or 5 classes? How many class columns are enough for this database? So to get rid of these repeating groups, we do it this way, by putting repeated entries into the table. And now the problem with this database in first normal form is we have redundant information over here. To get rid of the redundant information, we split it into a couple of tables. And so this is looking more compact, less redundant, but there's still a problem. And that is, in the student table, we have a key here, and we have a column that's not dependent upon the key at all. So Dave's office number has nothing to do with Skylar. And so to get rid of this problem, we create another table, and at this point now we're in third normal form. So in order to collect information about an individual student, we perform a join. And a join combines data from two or more tables, and it is, in essence, a process of denormalization. So looking at the properties of the transactions associated with relational databases, it goes by the acronym ACID. Have you talked about the ACID properties? Okay. ACID stands for atomic. The relationship or the transactions have to be all or nothing. They cannot be divided. Consistent. Transactions transform the database from one consistent state to another consistent state. Transactions are isolated. Each transaction executes independently. And finally, they are durable. Changes are preserved even in the event of power failure or crashes or errors. The database captures those changes and remains in a consistent state. So we're going to take a little bit of a detour now to talk about big data. So in 2014, there were over 4 million Google searches, 2.5 million user shares on Facebook, 277,000 tweets every minute. And this doesn't even take sensor data and biological sequence data into account. So by 2020, here's a chart that predicts how much data there's going to be in the data universe. So these numbers represent the number of exabytes. And an exabyte is 1 billion gigabytes. So the estimate is that by 2020, there are going to be 40,000 exabytes of data in the digital universe. Now, this is 40 zettabytes. Now, a zettabyte is 10 to the 21st. So if you're from the US and using the long scale, that's a sextillion bytes. If you're from someplace else in the world and using the short scale, that's a trilliard of bytes. And zetta was added to the International System of Units in 1991. So, but here's something else. This was the prediction in 2012. It's 5 years old. This was before the advent of nanopore sequencing. And Dave and I were having a conversation this morning. And the current sequencing rate for a nanopore sequencer is 1 million bases per second.
1 billion.
1 billion?
Oh, the current version is 1 billion. The next version will be 1 billion.
Yeah. But you were saying that there would be a gigabyte in 15 minutes? Yeah. So anyway, the question then becomes, what are we going to do with all of this data? And the answer is, if you think about it, of course, the only thing that we can do with it, we're going to throw it away. And so the question then becomes, are we going to capture the important information in that data before we throw it away? And so this is something that Dave and others here have thought a lot about. And we have some ideas how to address that. But that's kind of outside the scope of this lecture. But if you're interested, I'll be happy to talk to you about it. So with big data, we talk about the 3 V's. Volume. We're moving from gigabytes to petabytes, and as the previous slide indicated, to zettabytes and beyond. Velocity, sensor data, financial data, social media, biosequences. coming at us faster and faster all the time, and variety. Data are in many different formats, many different types of data, and the situation is only getting bigger and more complicated all the time. So the requirements for dealing with big data: we need a fast, reliable response. Our response needs to be flexible enough to support various data types and formats, and there can be no single point of failure. So coming back to relational databases in the world of big data. Relational databases are not designed to handle change. Here's an entity relationship diagram, and this is actually a pretty small one. But you see in here all of the tables involved in the schema for this database and the links that indicate how you can link these tables together with the keys. So the schema, the data models, can be very complex. The modeling of the data needs to be done in advance. It's very hard to change these schemas, and the changes may require, in addition, significant modifications to applications. I read a prediction by one large corporation that had a very complex, extensive database. They predicted that to add one column to an existing table would cost $1 million. And so they're not very flexible. So they're also not designed to scale. They were designed to run on a single server, to maintain integrity of the table mappings, and to avoid all of the problems associated with distributed computing. There's been a lot of attempts to improve scaling for relational databases: master-slave models, replicated, sharded, which is divided and distributed data, shared storage, in-memory processing, and distributed caching. These have been more or less successful in some cases. But here's a diagram brought to you by the people that developed MongoDB. So you have to be a little suspicious of this, but it basically says that as the volume of data increases, if you have a NoSQL database, your performance stays consistently high. If you have a relational database, then performance drops off to eventually 0. So relational databases are good for managing small to medium amounts of structured alphanumeric data, data sets that are continually updated. In this case, normalization is a really nice feature to have, because the updates to your data can be made in one single location. They're good for ensuring data integrity, for complex ad hoc queries, and for structured data that has a very static schema and where your join depths are not very deep. So relational databases are not so good for managing large amounts of unstructured data. Okay, so now we come to talking about SQL. SQL stands for Structured Query Language. It is the de facto standard for querying relational databases. It's been around since the mid-1970s. It followed along soon after Ted Codd developed his relational model for databases. It's simple and easy to learn, but it does not adhere entirely to Codd's relational model, and he reportedly didn't like it very much. So here's an example of a SQL query. So we want to select everything from the customers table where the last name equals Robeson. I don't know where Mike is. He was going to be here. But anyway, this is the kind of information that we get in return. So last name matches, and it gives us additional information that's in the customers table, or customer number, last name, and first name. And that's as deep as I'm going to go into the actual SQL language. But now for NoSQL. So NoSQL means not only SQL, and it refers to non-relational databases. So SQL is a programming language. NoSQL is a class of databases. So I found a definition in the Data-Driven Perspectives book by somebody named Bob Wakefield, and I thought it was pretty close. It's an ill-defined set of mostly open source databases, mostly developed in the 21st century, and mostly not using SQL. And here's an example of some NoSQL databases. And I'm going to talk about 3 of those. So how to write a CV to leverage the NoSQL boom. So do you have any expertise in SQL? No. So they think about it for a while. Doesn't matter. Write expert in NoSQL in your CV. So contrary to popular belief, NoSQL doesn't mean NoSQL. It means not only SQL. So we need to talk about the CAP theorem. Now the CAP theorem says if you want consistency and availability and partition tolerance, you can only have 2 of these. Now, the first 2 are obvious. Partition tolerance basically means you can cut up your database into lots of little pieces and distribute those pieces out among different processors that may be very widely distributed around the world, and the database will be tolerant to that partitioning. And so partition tolerance basically means they are scalable. So consistency means all clients always have the same view of the data. Availability, all clients can always read and write. Now, the databases that fall into this category, consistent and available, are the relational databases, but also Neo4j, which is a graph database that we're going to talk a little bit about later. So, partition tolerance, the system works well despite physical network partitions. And databases that fall into this category are Apache HBase, MongoDB, which we'll talk about, and Redis. Now, in the availability partition tolerance category, we have databases like CouchDB, Cassandra, and React. And the CAP theorem says there aren't any databases in the intersection of these 3. So the main takeaway from the CAP theorem is if you want low latency and scalability, you need to choose partition tolerance. And then there's a trade-off. You can have either consistency, where all clients always have the same view of the data, or availability, where all clients can always read and write. So the question then becomes, what's most practical for your application? Now, here's how to take advantage of the CAP theorem. The teacher asks, where's your homework? And the response is, I can give you a half-done version now, availability, or a fully done version tomorrow, consistency, but you can't have both. So I found there are really a lot of cartoons out there about databases, and some of them are pretty interesting and informative. So here's a father-daughter conversation that's about to take place. So Dad calls Sandra over, and he wants to tell her something very important. And here's what he says. If data consistency is business critical, then no SQL database will be the wrong choice. And she, of course, promises never to forget. But here's a quiz question. What's wrong with this advice? Remember the CAP theorem. We talked about consistency, availability, and partition tolerance. And you do have databases where you see a consistent view of the database. And so consistency, lack of consistency does not necessarily follow from a NoSQL database. Okay, NoSQL properties. So remember ACID, those are the transaction properties of relational databases. These are replaced in NoSQL databases with ACID is replaced with BASE. Pretty clever, huh? So BASE stands for Basic Availability. The database appears to work most of the time. The soft state, data stores don't have to be write consistent, nor do different replicates always have to be mutually consistent. And eventual consistency. So given enough time, consistency will propagate through the database so that if you leave it alone for a while, eventually everything, all the information in the database will be consistent. So start.
Has that ever happened?
That you leave them alone that long? Yeah, probably not. But we're going to look at a database called Cassandra. Cassandra is an available, partition-tolerant database. So, some preliminaries. Okay, what's up with the I? So, if you look at Greek mythology, Cassandra was a seer. She was given the gift of prophecy by the gods. And then the gods got mad at her, so they gave her a curse that no one would believe her. And this, of course, drove her mad. So it may be that the takeaway is one ignores Cassandra at their peril. Or perhaps there's a connection to the oracle at Delphi, another seer for whom a database is named. Or the message might be that NoSQL databases of the future, inevitable of the world of big data, that there's denial from the traditional relational database community. So I couldn't really find a definitive answer out there for where the name Cassandra came from. Okay, Cassandra is massively scalable, open source, distributed database written in Java. It's a hybrid of Amazon DynamoDB, and Google Bigtable. It's masterless with no single point of failure, and it's designed to be fault tolerant with automatic recovery and 100% uptime. So here's the hierarchy in a Cassandra database. You have nodes. Nodes are collected into data centers, and a data center is just a logical grouping of nodes that can be separated from other nodes. And then data centers are organized into clusters, and a cluster is just all of the nodes. So all of the nodes are the same. It is masterless, no master. All nodes participate in the cluster, not just the local data center. Nodes can be added or removed as needed, and this can be done on the fly. Nodes communicate across the cluster through the gossip protocol. More about that in just a second. Data is partitioned among all of the nodes in a cluster, and there is custom data replication. So the gossip protocol, very aptly named, it's a peer-to-peer communication protocol that runs every second. Each node exchanges information with other nodes about itself and about nodes that it knows about. And with up to 3 other nodes. Messages have a version, so older information is overwritten. So eventually, as this gossip protocol spreads across the entire database, the information gets propagated eventually to the entire database.
Is this similar to Bitcoin in that regard? Does it vote among the nodes?
I'm sorry, that.
Is it similar to Bitcoin? Does it vote among the nodes?
Yeah.
Okay.
Yes, it does. And it, well, I'll talk more about that in just in a slide or two. So, so the client reads or writes to any node, and then the node that it writes to coordinates with other nodes. Data is read or replicated in parallel. So in this case, we have a replication factor, abbreviated RF, of 3. And so each node, since the data is replicated 3 times, each of the nodes in this cluster of 5 will store 60% of the cluster's data. So this is actually pretty small for a data center, and so so this number is usually much smaller than 60% of all of the data. So consistency. Cassandra doesn't totally ignore consistency, but consistency is tunable, which means that the client specifies consistency, the consistency level desired for each read or write transaction. And so there are a bunch of different options that the client can specify. These are 4 of them. All means you want consistency across all replicas. Now, you don't want to specify all the time, because then basically you're forcing Cassandra into a completely consistent database, which will end up really significantly degrading performance. So 1, you're happy with 1 replica being consistent. In the trivial use of the word consistent. Quorum, more than 50% of the replicas, or local quorum, 50% of the replicas in the local data center. Now, an example of this is we write to the data center, and we specify the quorum level of consistency. So this node does a parallel write, and since our replication factor is 3, it writes, it makes 3 copies of that data. Now, it gets an acknowledgement back from node 1 in 5 microseconds, acknowledgement back from node 2 in 12 microseconds. At that point, we've reached a quorum, 2 out of 3. And so the acknowledgement goes back to the client, and then at some point, perhaps much later, an acknowledgement may come from node 3. So does that kind of answer your question? Okay. So reliability. So with a proper tuning of the replication factor and proper use of the consistency level, a Cassandra system can be extremely robust with respect to different levels of failure, unaware of nodes taken down for routine service maintenance, or even the loss of entire data centers. So a couple of interesting quotes here. Here's one from Netflix that says, let's see. Yeah, Cassandra dealt with the loss of 1/3 of its regional nodes without any loss of data or availability. So there's a company called Outbrain that is a content discovery and marketing platform that during Hurricane Sandy, they lost an entire data center. The application failover resulted in us losing a few minutes of serving requests for a particular region of the country, but our data in Cassandra never went offline. And so that's what Cassandra is designed for. Now, here are some quick examples. So this is 3 data centers spread around the world. Active, active, active means that they're all running at the same time. So routine maintenance, nodes are taken down. The application is totally unaware of this because of the replication factor and the fact that nodes can all communicate with each other. So here's an example where there's a tier failure of the application services, and traffic can just simply be rerouted. Similarly, if there's a loss of an entire data center, rerouting can take place where this application services that is aware of the other data centers can be switched to remote access. And if you lose your wide area network between a couple of data centers, then the consistency level could be affected in such a way that it's going to take longer for your system to become consistent. So the speed of Cassandra, looking at some data for a read-write mix workload and various number of nodes. So for MongoDB, there was a little bit of an improvement in operations per second as you increase the number of nodes. For HBase, a bigger improvement, but for Cassandra, we have almost linear speed up. So almost linear. This is a linear scale. This is a log scale. So this represents almost linear speed up in the number of operations per second. So programming Cassandra. It's a programming language called Cassandra Query Language. So SQL looks a lot like SQL. And a quick example, it has select statements that look just like SQL, create, drop, insert statements. Quick example here. Oh, but it doesn't have joins because it's denormalized. So you can create a team, a table. Here's one called teams, and you have various fields in that table. You can do an insertion into the table, and it turns out I got Ben Zobrist's jersey number wrong, and so here's an update that you can make where you correct it. So it looks a lot like SQL. So Cassandra, how's it being used? So some examples of companies that are using Cassandra. AOL for article browsing. Spotify for queuing up playlists. So recommendations, personalization engine. Eventbrite, which is a company that organizes events and it's a way to sell tickets and so on. So it can personalize the suggesting of events of interest to an individual. Outbrain we saw before, it's a content discovery platform. And Netflix is using Cassandra to make viewer recommendations. Sensor data and the Internet of Things. So the Internet of Things, high velocity time series data is going into Cassandra. NREL, National Renewable Energy Laboratory, where Dave's good friend, Martin Keller, is the director of the laboratory. They're using sensor data in the Cassandra database. Messaging, Comcast is presenting viewer alerts through the TV. And fraud detection, the Internet Identity Company is developing defensive and preventive measures for security. And so Cassandra, if you're interested in how many likes the latest Justin Bieber tweet has, it doesn't really matter too much if it's 4.1 million or 4.2 million. So all of the clients, all of the users are not necessarily going to see exactly the same value. And that's what is characteristic of all of these different things. If it's not an entirely consistent view to the user, then it doesn't really make much difference. If there are 25 recommendations from Netflix for a particular viewer, and there's really a 26th one out there, eventually it's going to show up, so it doesn't really matter. Yeah.
Yeah.
Yeah. Okay. So moving on to MongoDB.
So why would you not want to use Cassandra?
Pardon?
Why would you not want to use Cassandra? Facebook uses it, so what's wrong with Cassandra? Why would you not want to use Cassandra? Or when would you not want to use Cassandra?
It may be that consistency is more important than availability. And so,
Like for medical records?
could be.
Maybe, maybe
But-
not.
Should I give this drug to this patient? Maybe not.
I'd go with that one.
Yeah. So MongoDB, the name comes from humongous, which most of you probably know. It means huge or enormous. It dates from the 1970s, almost exclusively in the US, and it's possibly based on huge and monstrous. So MongoDB was developed by a company called Tengen, starting in 2007. It is a document-oriented database. It's hash-based, it's schemaless. There is no data definition language for MongoDB. In practice, this means you can store hashes with any keys or values that you choose. The application needs to be aware of the schema and the mapping, and it uses BSON, which is a binary format that's based on JSON. It's written in C++, and it supports APIs in many different languages. This is just a few. So it is document-based. So we have a document. In the document, we have fields. Documents are organized into collections, and collections into database. So compare this with a relational database. So at the highest level, they're both called database. Collections correspond to tables, documents to rows, and fields to columns. So there's two ways. Let's look at an analogy of medical records. There's two ways to organize medical records. So you can put documents of the same type together. And so you can have a drawer where you keep all medical histories, another drawer where you keep information about all your patients' medications, another for labs, and so on. And then you have an index that tells you where to find the information for a patient of interest. And so you search in this index, and for patient number 42, you locate a number of records. And then you collect these records for that patient. So this is one approach. So another approach is you group all related records together. So you have patient 1, patient 1's records for 2, 3, 42, and so on. And then when you need information about patient 2, you just grab that set of records. Now, databases work the same way. Relational databases divide things up by type. So there's a table for history, one for medication, one for labs. Document databases group all of the information related to a particular, in this case, particular patient together. And so you have a data model for the relational database that looks something like this. For the document, your model looks more like this, which leads to a JSON document that looks like this, where inside the information about the patient, you have information about ID, name, birth date, whether they're still alive or not. And then in history, you can have as many different records in there as you like, medication, information about drugs, and so on. Now, this is a great way to organize the information, but of course the application that uses this database needs to be aware of how the data is organized. So the architecture for a MongoDB database looks like this. Now the various pieces of this, there are a number of shards. It is partitioned into these smaller, faster, more easily managed pieces that are called shards. Sharding and sharing data between shards is completely automatic. MongoD is the primary daemon process for the MongoDB system. MongoS is a routing service for the shard configurations, and it processes queries from the application layer. Each configuration server holds a copy of the metadata that indicates which shard contains which data. I guess that's the end of that slide. So how is MongoDB being used? So Oxford Nanopore has a big MongoDB database, and they characterize it as building the Internet of living things with MongoDB. And there's a very nice presentation out on the web from Oxford Nanopore. The Broad Institute is using MongoDB, making connections between genetics and disease. Cisco using MongoDB to power their WebEx social app that they call the Collaborative Workspace. The U.S. Department of Veterans Affairs, the VA, is using it for one logical federated data store for all types of VA data. And they currently have 400,000 users and over 5,000 applications using their MongoDB implementation. The Weather Channel, they're very interested in distributing weather alerts in real time to specific locations, and personalized travel discovery with Scratchpad from Expedia. Now, how would you characterize this set of applications, thinking about how MongoDB is defined? So remember that consistency is much more important here, perhaps, than absolute rapid availability. And so you need to get things right. So you want, for weather alerts, you want it to be correct. If you're pulling out medical records at any time, you want to make sure that they are the latest, up-to-date medical records, the best information that you have at that point in time. So one more database to go, and that's Neo4j. Neo4j, we're going back to consistency and availability, and we'll talk a little bit about scalability for Neo4j in a minute. But where does the name Neo4j come from? Well, there are all these theories out there online. There are some people that say it stands for new energy for objects, or network engine for objects. And 4J stands for Java. But it's really all about Neo fighting the matrix, also known as the table. And so it's the NoSQL databases fighting against relational databases. So here's a description of a graph database with a graph. So a graph has components. One of the components is nodes, another is relationships. And relationships are used to organize the nodes. And both nodes and relationships have properties. So here's an example, a library data model. And so we have a node with a name. and another node with a title. And so in this case, the relationship between those two is that John Le Carre wrote the book Tinker, Tailor, Soldier, Spy. Here's another example. Graham Greene wrote Our Man in Havana. So then we have some readers down here. And Sayron likes Tinker, Tailor, Soldier, Spy. Meredith likes both of them. And so the nodes store entity information. The links connect nodes and connect nodes and they structure entities. A link is the equivalent of an explicit join. And so it takes the place of a join operation in a relational database. And then we have properties associated with both the nodes. So for this node, it has a title and a published date. And in this link, we have a date that Meredith indicated that she likes that book. So beginning with version 2.0, which was about 3 years ago, I think, they added labels. And so you can label a node with multiple different labels. It allows for the efficient creation of subgraphs. One of the things that was kind of difficult in the early version of Neo4j was you had to specify some sort of a property inside the node indicating what type of node it was, or you needed a definition node like for what a book is, and then have all of the book nodes point to that definition node that contained meta information about that type of node. And so the labels made things a lot easier. So a word about scaling in Neo4j. So Neo4j is a consistent, available database. And so according to the CAP theorem, it cannot be partition tolerant. So how does it scale? Well, a single instance of Neo4j can have 34 billion nodes, 34 billion relationships, and 68 billion properties. So you can make a pretty big graph from with Neo4j. But if you look at the documentation for Neo4j, they have what they call a scalability package, but it's known as high availability. Now this is a little bit strange because scalability has to do with partition tolerant, and that's something completely different from availability. And this is the idea behind there's a load balancer. It's a master-slave type arrangement. But what they tell you is that the full graph is replicated to each instance of the cluster. And cluster management, the cluster management component continuously stays in sync with all instances of the cluster. And so the full graph says the graph is not really partitioned across clusters. And if the cluster management components are constantly syncing things up, then there may be a small loss in consistency across different clusters. So it looks like scalability is more focused on high availability rather than than actual scaling beyond a single instance of the database. So querying the graph. So Cypher is Neo4j's language for querying and updating graphs. It's a declarative language that has a structure in some ways similar to SQL. The structure is similar in some ways, not the syntax. It specifies what to retrieve from a graph rather than how to retrieve it. A query of a database graph is a graph traversal, and it begins at a specified set of nodes. It follows specified links to a set of nodes, and then continues along the traversal until the query is completed. And then properties from the nodes along the path can be retrieved and reported back. And so queries contain this pattern. And I color-coded these so you can parse the queries a little more easily, where the nodes, sets of nodes, are in green, the links are in red. So you have nodes linked to nodes. Now, if you care about the direction of the link, you can put an arrow on it. And if you also care about the type of the link, you can specify what type of link you want to traverse. So remember the library data model that we looked at before? So it turns out that Seiron is looking for a good book. So step one is find people that like the same books that she does. And so here is a query to do that, a graph traversal. So you specify the starting node, and you specify that by saying, by giving a property of that node. Now, this may not be a unique node, maybe a set of nodes, but that's okay. And we're going to give this node a name. We call this begin, so we can refer back to it later. So, yeah, we name the node. So we start here, and if you follow up on the graph above, you can see this is our starting point. So from that point, we follow the link likes, and that takes us up to this node. Now from that point, we follow this link in the reverse direction. So you can follow a link either way. We're following this link, but we're going backwards across that link. And so we get to this point, and we give that node, that set of nodes a name as well we call good reader, and then we return the begin name and the good reader name, and we end up with this information. So with this particular query, Seiron has a list of people that like at least one of the same books that she likes. So taking it a step farther, find the books that these people like. And so we add this additional, this is essentially the same query. We add this additional link at the end to get back to the books. And following that along the path, we go from this node to that node to this set of nodes to this set of nodes, and then we return the book name and say Ron has found another book that she may be interested in reading. So, case study in using Neo4j, and this is actually a study that I did using EcoCite. EcoCite is it's a database that describes the genomic, metabolic pathways, and regulatory network of E. coli. And the data is stored in tables, and the tables look something like this. So this is one entry from a table called genes, another table down here called proteins, and this table up at the upper right is protein ligand complexes. So if you start looking within this data, the unique ID is something that we can use, pull out and use for a node ID. So here's the common name of this particular gene. We can use that as a property of that node. And then down here, we have an entry called product. We can use this information as a link of type product to another node. And so in the proteins table, we find the definition of this unique identifier. And it actually appears a couple places in the protein database. So once in the type that's just a single protein, polypeptides, and down here in protein complexes. And so other connections that we can find there are this connection that says that this protein complex is a component of this protein ligand complex. So anyway, there's just all of these connections that you can find between the tables that you can extract and use to build a graph database. And so this is just a small subgraph of the EcoCyte graph that captures that information from those entries that we were looking at, where this particular gene has this protein product. This protein is a component of this protein complex, and the component link has a property that tells us how many of this protein is part of this complex. This protein complex is a part of the protein ligand complex, and the other component is this compound, the cyclic AMP. And so just an idea of how you can go from this tabular information to a graph database. So here's a picture from the Neo4j browser, and you probably can't read anything on it, but the idea is that once you start putting all of this information together, and you put information about regulation, enzymes, reactions, cofactors, and so on, the metabolic pathways in E. coli just emerge from the graph database once you organize things in this way. So another example, a case study with Medicare data. So several years ago, Oak Ridge had an agreement with the Center for Medicare and Medicaid Services to work on organizing their data. And so they gave us all of the Medicare and Medicaid CHIP, and there was another database called PACOS for the state of Texas, and we organized that into a graph database. And here was just a provider subgraph, the model that we used, the information that we tried to capture about each provider, phone information, address information, and then we wanted to organize providers by state, sometimes by city, by a specific zip code, and we split those out into individual nodes so we could connect every provider in Houston, for example, together. Then there was information about Medicare specialty. I can't even remember what some of these things stand for. You can probably tell me. But,
So the NPI is a national provider number.
yeah,
I don't know what the PAC is.
yeah, I can't remember either. But so by far the most difficult part of the project was cleaning the data. And this is often going to be the case. So apparently entry of Medicare data is free form. So there are no controlled vocabularies. And so you find very interesting things. Like Houston can be spelled at least 31 different ways. And there are more than 100 states, including Africa and Canada. And so we didn't really attempt to clean up the data other than in the case of misspellings of certain cities. We could kind of figure out what they were from zip code information sometimes. But when you had zip codes that were, 6 digits long or 10, or some weird number of digits, it was pretty hard. So there were some really interesting things that we discovered. Graph traversals with Cipher, just like we did with the library model, uncovered some interesting anomalies. Like we could look at node degree. That's another specification you can put into a Cipher query, that you want to zero in on a particular node or set of nodes and then tell me what the degree of that node is. In other words, how many connections are there to that node? How many links of a particular type? And so we discovered there was one provider who was a member of 22 different medical groups. I don't know how common that is, but that seemed to be a bit of an outlier, a little suspicious. So there was another provider to look at discrepancies and addresses. There was another provider who worked in Waco, which is a town in Texas, and lived in Lesotho, which is a country completely surrounded by South Africa. So just a couple of very suspicious things that we found in the data. Now, it turns out that the people from CMS weren't really very happy with what we were doing because we were plugged into the wrong place at CMS. We should have been plugged in at a higher level. The people that we were talking with really wanted us to do something that would make their job a lot easier. And instead, we gave them something that potentially could make their job a lot harder. And so, but lots of good information and a really nice way to discover anomalies and potentially even fraud in the Medicare, Medicaid system. So these are some actual screenshots that we took from the Neo4j graphs associated with this, and you can see here some information about a beneficiary, a particular beneficiary, and over here there's location information, so we could collect all of the informations about beneficiaries in a particular city or zip code. Over here, there's information about who this individual's Medicare carrier was, and here's an example of a prescription for that individual. So we could pull up essentially their whole medical history and all of the different drugs that had been prescribed to that individual. down below, now these are not different graphs. These are all small subgraphs from the entire single one large graph that we built. So information about a particular provider who you can see is a physician for this particular Medicare carrier. Medicare carrier, by the way, is a private company that has been contracted to provide Medicare services for individuals. Did I get that right? Okay. So over here and over there, we have a couple of different hierarchies that we put together. ICD-9 codes, most of you know about ICD-9 codes, and ICD-10 codes were not out yet at the time. But this is ICD is International Statistical Classification of Diseases, and it's a hierarchical set of categories. Over there, Healthcare Common Procedure Coding System, and so lots of information about specific illnesses, and we could go to a specific illness associated with a node and then look out at all of the set of individuals that are, for whatever reason, connected to that illness. And then finally, the Neo4j graph viewer suppresses a lot of information. Otherwise, it would be completely unreadable, because this says that this particular procedure described by this code was performed, and it points to 767 other nodes. And so a lot of information, and that's very appropriately suppressed. So one other graph database that we designed, and it was for the Cancer Genome Atlas, the BRCA, breast cancer data. And this is ongoing. It's kind of in a hiatus right now, but we designed and built the database. But first of all, we needed to figure out what are the nodes that we needed, the different entities. And then what are the properties of those nodes? How are they linked together? And then what are the properties of those links? And then I added to this, just once we built this, what the counts of all of the nodes are. So it turns out that the really interesting stuff is happening right here in this part of the database, because we're interested in copy number variation. A lot of times in cancer, instead of having two copies of the chromosome, at some point you'll have one copy, or maybe no copies at all, or 3 or 4 or more copies. And so copy number variation can give you a lot of information about the cancer. So we needed to actually code that information as a property of a link from a data group. Now, a data group is a term that comes from the Cancer Genome Atlas, but you should think of it as a set of data for a particular patient. And if you follow the link up to participant, there were over 1,000 participants, but 2,200 different data groups. And we would have data from different tissue samples for individuals. In most cases, for a participant, we would have data from cancerous tissue, and a sample from normal tissue. So then, in this group of information about the tissue sample, we would look at the number of copies that we had, and then we would figure out, we knew where in the chromosome that particular copy number was, and then we would look what are the genes that were located inside that region, and then we would map to those genes and label this with the copy number. So we're also interested in, down here among the genes, in figuring out, if we have a particular copy number, what does copy number of the previous gene look like? What does the copy number of the next gene look like? And so we may want to use this link to kind of move along the chromosome and look at one gene and then the next gene that's physically located on the chromosome. And so we did some very preliminary work with this and got some interesting initial results, but we, as I said, it's kind of on pause now, and hoping to get back to it. So Neo4j databases, who are their customers? So Walmart is one of the customers, and they call their use of Neo4j optimizing customer experiences with real-time recommendations. So this one I find really interesting. It's the International Consortium of Investigative Journalists. So a few years ago, there was all of this information that was leaked from a Swiss bank. There were 60,000 files on 100,000 individuals. And so just this huge amount of information. So the ICIJ took all of this information. It was one of the largest journalistic collaborations in history. And they went through these documents and linked all of the information into a graph database. And then with this kind of organization, it was much easier for them to discover connections between companies. There are a lot of shell companies out there that are set up as tax avoidance vehicles. And so these links between companies could very quickly traverse through this graph and figure out, where is this really connected to? Who are the individuals that are involved? And so they were able to really extract some very interesting information. There is, I think, online actually a website where you can go in and put in some queries and pull information out about what they've discovered in this database. So there's a company called Orange that has used graphs to model their IT systems, and then they, if they have very complicated configurations, and they use these graphs to search for potential security issues in their information systems. This one's also very interesting. NASA is building a graph database for unstructured data. They have 50 years of lessons learned and conversations with astronauts on the International Space Station. And so they can take these conversations and have links for certain keywords or certain phrases in the conversation and link those up to different astronauts and then maybe have some information about how well the astronauts coped with certain situations and so on. And so they can very quickly zero in on information, perhaps some telltale signs that we need to get this guy off the International Space Station as quickly as we can. But it's when I first saw that NASA was using Neo4j, this wasn't what I expected at all, but a really interesting application. So eBay is actually using it. eBay recently, well, I don't know how recent it was, but bought an e-commerce delivery service. And so they're interested in figuring out how can they most quickly route the things that people buy on eBay to the customer. And they came up with a Neo4j solution that they say is thousands of times faster than the MySQL solution, required 10 to 100 times less code, and had added functionality. And so if you think about it, this is something where there's an underlying geographical model where you're connecting cities by roads and so on. So a graph database is very natural for that. You've got an underlying geometry associated with IT systems. In this case, you're taking documents and pulling information about different entities from those documents and linking that information together. And so all of these turn out to be very nice and interesting applications for a graph database. So that's it. Any questions? Anything you want to talk about?
No, I want to give these guys questions.
Yeah.
So, I have a question about the Neo4j.
Yeah.
So, saw you show the node of the ICD9 one. So I want to see if you try to add the more data of ICD10, right? It means that you need to connect all the nodes after that. In terms of writing some new node, introducing new node to the
you're right. So my response to that would be that the ICD9 code databases are not very big. And so when I was creating the Neo4j databases, I ended up writing a lot of code that would just go through and parse data sets and pull information out and organize nodes and give them unique node IDs and then hook those IDs together with links. And so, and then when there would be a modification to the information, all of the Neo4j applications that I have used have been small enough that it's pretty easy to run these parsers, reload the information into Neo4j. And this works pretty well when you have, even for the Medicare and Medicaid data, pretty extensive. We could parse the data anytime we would, for example, figure out some way to better interpret these free-form addresses or something, make a change to our parser, run it again, and reload it. And that was pretty straightforward. Now, if you have 32 million nodes in your graph, I don't know if I should do it that way.
Yeah, I ran into this problem before. Let's try to create the node for the protein and PPAM.
Yeah.
Yeah. even the PPAM itself is pretty small,
Yeah.
16,000 nodes. But when they link to 300 million proteins,
Yeah.
it's a lot and take.
Yeah.
Maybe I implemented the wrong way and just
So
something happened.
that's a very interesting application. Let's talk about that. And I don't have an answer for you, but I do think that putting PFAM domains into a graph database.
What role do you see security playing in the CAP theorem? As far as does the trade-offs, specific trade-offs, also result in lesser database security? You see more vulnerabilities with specific trade-offs, and does that play a role as maybe a fourth item in the CAP theorem?
So you would certainly expect, I would certainly, I don't have a good answer to that, but I would expect that in a sharded distributed database that you would have more security issues than you would in the database on a single system.
Or just, I don't know necessarily more. I mean, if it's started yesterday, more opportunities that it has to do, but if it's all in one place, it's also another.
So,
It's a different type of risk.
yeah,
They both have security problems.
I mean, at Oak Ridge, we have a computing system that, I think there's just hundreds of thousands. And so,
But that's not what I guess. But people from universities can get time.
they can, the fact that, it's
You do nuclear simulation.
it's
Obviously,
it's a distributed system that on a graphically distributed.
and then there's the other computer. If you got water cooling. So there's the Titan, which is public, and it has what, 6 or 8 water cooling towers. And then there's the other building, Homeland Security. It's got what, 15 water cooling towers that you need security clearances to control. You see all of these. There's a nuclear power generator and a dam and all this other
But,
that's pretty secure.
Just from the databases you showed up there, every one of them, I was thinking, okay, well, that had a breach, that had a breach, that had a breach, that had a breach. And so I was wondering if the more we try to leverage these specific CAP efficiencies, the more insecure the data becomes.
yeah, I think that's certainly true. And, as I confessed at the beginning, the first 3 courses was more like a book report. And there were frequent mentions of security in what I read, but a lot of it simply said, a lot of the literature simply said this is security. There are probably a lot of applications that don't need to be terribly secure. There's not, I think that a lot of the Cassandra systems, for example, if you don't store personally identifiable information in the system, then
Facebook uses.
So for the security issue, I think we can apply some of this like quality there the blockchain system?
Yeah, but the thing with the blockchain system, when you mentioned that, it's the first thing that I thought of, but it has a built-in reward system for the miners to keep it. You understand, there's no, or like if we were going to run a biomedical database, we're not going to pay people to go in and implement security by voting on. You understand, we don't have necessarily it works if you provide motivation for people to self-police, but not necessarily in other applications. That's the only downside I see of the blockchain and that sort of method of keeping a decentralized database secure.
The medical records, that's what it is. For me, listening, it's almost those 300 million versions.
Good luck transferring 5 terabytes with the data.
That's what I'm saying. It's a lot of those. I didn't see any banking applications up there, but the ones that aren't, absolutely security essential. That's then they're great solutions.
Yeah.
But if we're dealing with patient data, then we have to kind of put that in the mix.
We have been thinking about that with respect to the Veterans Administration data, because for the last couple of years, Oak Ridge has been working with the Veterans Administration to build a secure enclave at Oak Ridge that will house all of the VA medical data. Now, it's going to be distributed across many different processing units and memories and so on. But it all sits inside the same secure enclave. And I think the medical record is probably going to have that same situation most of the time, where all of your medical records are going to be physically located in the same place. They may be designed as a NoSQL partitioned database, but unlike some of those examples with Cassandra, you're not going to have your database all over the world. That one single location. But there are real advantages to going to a NoSQL database. Even if it physically resides in the same location.
Yeah, because one of the first things with the VA is this accessibility issue, because they've got hundreds of petabytes.
Yeah.
And just being able to read those records. There's no way you can make a relational database. You can even know SQL. You can do that in Janet's first try. Some of the first queries, the ones that really take months. Okay, this is well, it's like about that months. It's about
Thank you very much.
You're welcome.
That was awesome.
so how is this other
Separate.
No, the art rights.
And you can do your own. That's awesome. Thank you so much for doing that.
Yeah, you're very welcome. It was fun for me.
Okay, I'm going to get you out of Blackboard. And
When you were up here before, I kept trying to hide that Duke picture from you, so I'm surprised.
yeah, no, I didn't. I completely did not see it. Completely did not see it.
So I just